So we're going to start with this page 26. These are non-calculator, so you need to graph by hand. When you graph an exponential, first focus on the base. It's going to tell you two coordinates to start us off with. It's going to tell us that 0, 1 is one of them, and then the other coordinate is 1, 2, base. So you can mark them here, 1, 2. And then the exponential parent graph looks like this. Okay, then you want to talk about the transformation. Talk about this one first. That negative will reflect it over the x-axis. The 4, then we'll just move it to the right 4 and up 1. So we're going to take these two coordinates and then we're going to flip them over the x-axis. So this one flips here, this one flips here, and then the whole curve flips and it's here now. After that, you want to take these two coordinates and move them right 4 and up 1. So 1, 2, 3, 4, 1. 1, 2, 3, 4, 1. Before you draw your final graph, draw where the asymptote got moved. Now they originally start with a y equals 0, but now it got moved up 1. So the asymptote now is here at that spot. You then can curve this. It should curve like this one, but just over here. And that's your graph, leveling at the asymptote. Okay, now you can define your asymptote, y equals 1, because it's horizontal. The domain is all reals, and the range is y is less than 1. Okay, moving on to the next graph. This is at base 1/3, so it always starts off with that coordinate, 0, 1, and then it's going to be 1, 1/3, 1, the 1/3, which is around right there. That's going to cause the graph to shape like this as your parent graph to begin with. Transformation-wise, there's a vertical stretch of factor 2. Let's do that transformation. You're going to multiply the y coordinates by 2 here into that spot. Okay, and so let's move them by 2. So 0, 2, let's see, 0, 2, and 1, 2/3. 2/3 is like 0.66, so it's just a little bit higher. But so make it a little bit higher, and then it still curves the same way. So that's this vertical stretch, and then this is outside, not up there, so it's going to cause it to go down 2. Okay, so let's move it down 2. So right there, 1, 2, we're going to eyeball that, and then 1, 2 here. We're also going to move our horizontal asymptote down 2, so now it's here. And then this is our final graph. Okay, as far as the domain goes, all reals, it's slowly inching this way and that way. The range, y is greater than 2, above the 2 mark. Okay, let's do some log graphs here. So first thing with log is focus on that base. It should tell you two parent coordinates, 1, 0, and 3, 1. It kind of flips your exponential idea. So 1, 0, 3, 1. And the logs shape like this. Okay, then as far as transformation goes, this one's going to reflect over the x-axis. And then it's going to go left 2, up 5. So let's flip it over. This is on the axis of the x-axis, so it stays, but this one flips here. The whole curve flips over. So that's the first transformation, and now we're just going to move it left 2, up 5. So 1, 2, 1, 2, 3, 4, 5, 1, 2, 1, 2, 3, 4, 5. So the graph is going to be here, and before you draw your graph though, move your vertical asymptote that was here, 1, 2, so it's here now. And then this shapes just like this green one, but up here. That's the main one you want. So asymptote is x at -2. Domain is all reals. No, domain is not all reals. Domain is from 2 negative to infinity, or x is greater than -2. The range will be all reals because it's slowly itching down and going up. Okay, let's try this next one. So focus on the base. That tells you 2 coordinates. It tells you that we're going to start with 1, 0 and 4, 1. And then the parent one shapes like this. All logs shape like this. There's going to be a vertical stretch of factor 2 based on this 2. And then there's just going to be a down 3. So 2 transformations. Okay, so let's do the stretch by changing the y coordinates, multiplying the y coordinates by 2, this 2 here. And now you have a 1, 0 and a 4, 2. So it got stretched up a little bit. It still levels this way. And then everything gets moved down 1, 2, 3, 1, 2, 3. And it's still shaping this way. Okay, so domain. Well, asymptote, it's an x asymptote. It stays at 0, and then domain is x greater than 0. Range is all reals for this one. Okay, writing the expression in exponential form. So here we're just going to get rid of the logs if we want exponential. So we're going to raise it to a 5 base. That cancels this one. And this is pretty much your exponential form. This one's log, so we're going to put some log there, get rid of this exponential base, and we want to create a base 1/3. So take the log of base 1/3 on both sides. This rule cancels that, leaving you a -2 here. And now you have a log base 1/3 to the 9. Okay, when you go to evaluate, the goal is to just write it so that if you guys have like a log base 7 at 7x, these cancel, or 7 log 7x, these cancel, leaving you with the x's. So this one, this is a base 10, so you want to create 1 over 100 as a base 10. So you need to cleverly write it as, first bring that 100 up, and then you could say that 100 is 10 square, and then you guys have 10 to the -2, and then this rule cancels that, so the answer is -2. Okay, anything to the 1 is 0, and then these are already the same base, so there really is a power 1, so they just cancel, the answer is 1. And e and natural log written together cancel, so 5 is left. And then this one, we need to write 32 as a base 2. So then we're going to just start checking. 2 to the 4th power is 16. 2 to the 5th power is 32. So then those cancel, and 5 is left. Okay, we're going to break this apart. So this is all together inside the natural log. They're separated by multiplication. So the rule says to break it apart into addition, more logs, and then rewrite this as a half power, and then bring that half power to the front, and that will be your expanded answer. Let's expand this one also. We're going to start off with that big quotient, which separates it with a minus, 2 separate logs. And then each of these have a multiplication, so this one's going to break to a plus. And then this one, put a parenthesis here, because this one breaks up to 3 logs down here. Oh, and they're all log 5. Log base 5 to the 5, plus log base 5 to the y, plus log base 5 to the z square. Okay, now this is going to become 1. So you have a 1, and let's distribute that negative. This is also a negative. And then this is also a negative. And then this 2 goes to the front. So there's a 2 here. And that's your expanded form. Okay, condense. Let's do it 2 at a time. First, move that into a power. And then 2 logs separated by a plus can be combined as a multiplication. And then just move the next one down. This one you can combine and put this. Well, first move that 3 to a power. And then you can put this one. Let's square this underneath here. And then bring that one down. And then bring it to the power as well. And then I think I'm going to combine, just to save room, all of these have minus, so they're this part and this part, they're going to land down here. So the answer is 9x, y3, x4, z, like this. And then you guys can clean up the x here. So it looks like y3, x3, z. And that's the answer for that one. Okay, let's condense this one. Let's do these two. That's going to be a log 3 times 6. These are going to be multiplied times x. And then this is just going to be at the bottom. And then you can clean this up. 3 goes into 9 3 times. And then 3 goes into 6 2 times. So it cleans up all the way to log 2x. Okay, so then you guys get to use calculators now. So solving an exponential problem, you want to create common base. So I usually look for the smaller one and just try to test, like, try to create a base, but it's got to be too big. So that means these are probably going to be shrink down to like 9 or 3. So it's probably going to be 3. And so you can check around, but 27 is 3 cubed, and then 3 to the 4th power is 81. So when you solve exponential, you create common base, distribute that, and then now you are allowed to set the exponentials equal to each other, and then you can solve by subtracting and then moving that over. So you get this here. Okay, you can check by plugging it back in, and they should equal the same thing on both sides. Okay, if you get to problems like this, you can't create common base. So when you can't create common base, you just want to change it to a log and choose a log 7 to undo that. And then this one, you're going to change it to a log 6 over a log 7 with the change of base rule. And then you could just type this into your calculator. So natural log 6 divided by natural log 7 minus 2. Okay, this one, let's try to get the same base. So let's see. Let's start checking. 4 square, 4, 3. We're not going to get that. So maybe I'll try 2. So 2 to the 5th power, 32. So first, let's move 32 up. And then let's write 4 as a base 2 square. Then 32 could be written as 2 to the 5th power. So then you can multiply all of these together. That's negative 5 times that. So negative 5x and then positive 10. And now you created common base. So you can set the exponentials equal to each other and solve. Okay, so let me just check because that's such a weird number. So 4 raised to 3 times this number. And in the other side, I got 132 raised to the this number minus 2. And they're equal. So I guess that's the correct number. Okay, here, that's not really a base. That's just a multiplier. So start off by dividing by that 5. And then you realize you can't create base, so you're going to do a log 3 to get rid of that. And then this is done just like that. We're going to change it to a natural log base. And then the answer is when you divide it over. Okay, so type this into your calculator. Natural log 5 divided by natural log 3 divided by 2. And then go back and check and plug it back in here. Make sure it equals um, 25, which it does. Okay, so here when you have two logs and they're the same, you just set the arguments equal. These are the arguments of the log. And then you can work your way around to solve. Okay, when you check, just plug it in. Put the 3 here. It won't make this argument negative. That's fine. Plug the 3 here. That's 18 minus 11. It's positive. It's fine. When it makes the argument negative, it's an extraneous solution. Okay, when you only have one log, then your goal is to just get rid of the log by using a base on both sides. Take it to the third power, and then just kind of work your way around to solve for this. Okay, when you have two logs, you're going to condense it into a single log. Do multiplication. Keep your parentheses there. Distribute. And then you're going to undo the log by creating a base 2. So then it becomes a quadratic that we could try to factor or use the quadratic formula. Let's see, this one, let's do x minus 1 plus 4, and that factors. So you got two answers, negative 4 and 1. And then you can quickly check. This one's the extraneous solution because when you plug it back in, it makes the argument of the log a negative. And then the 1 will keep it positive. So the 1 is the answer. And this is the extraneous solution. Okay, combine these two log base 10s together. Multiply them out. So when we don't have a log here, it's log base 10. So we can raise both sides by 10. And 10 to the first power is 10. So then we'll move it over. And then get up to this point, we'll factor and solve. So then my answer is either 10 or negative 1. And then the negative 1 is the extraneous solution. So you can say extraneous, cross it off. Okay, so we got a radioactive element problem. First, to find the constant decay, we need to use this half-life idea. And so it's T equals 1620 for the half-life. So what you want to do is use this formula and let T be this and then cut A sub 0 in half. So if you have some unknown A sub 0, after 1260 years, you'll get half of that A sub 0 amount. So it doesn't really matter because you're going to first divide by A sub 0. And it's just going to cancel all the A sub 0. So you're just working with this. You can undo both sides by taking the natural log and then divide it over. So this is the value for k. Natural log 1 over 2 divided by 1620. And this is in scientific notation. We'll just keep it on our calculator. Remember that k value. Now we're ready to solve. So how much 2-gram sample will remain after 500 years? So now we have A sub 0 as 2, E, and then we have our k value times t, but I'm going to put 500 year there, and the goal is just to figure out this here. So we're going to type everything in. 2 times E, which is right here, raised to the k, so go up, highlight, times it by 500, and that's going to be what's left. So 2 grams shrinks to that after 500 years. How many year does it take 2 grams to decay to 8 grams? So they want the t. So now you have 0.8 grams, 2 grams, you have your k value, and you're solving for the t. So first divide by 2. Take the natural log of both sides. And then divide by the k value to isolate the t. So go back up and divide by the k value. So t is about this many years. Okay, we're going to try this next one. We have a compound continuous formula. So that's this formula here. That's the starting amount. So it looks like we're investing that much. We have an E. Compound continuously tells you it's this formula. 10 years later, his account balance is that. So we don't know the R. We know that T is 10. And we know that the P of T after 10 years is this much on that side. So first, we're going to start by taking this number, dividing by this number to get 1.1. Let me just double check. Okay, so then when we divide them out, we get to here. And then we can undo the E by taking the natural log of both sides. And then divide by 10. So R is 0.009, and percent is just, you can times it by 100, but it's 0.95%. So it's really tiny. So now that we have the R, they want the equation. So the equation is P of T equals this much E, and then we have our R, and then we have a T. And then here they just want T to be 20. So you're going to type this in and get the P of 20 years. So 200,000 E, pull out this R value, and then times it by 20. So about that much. Okay, last one. Let's finish this. So we have a social media year that has this many followers in 2020, and the page continues growing at this. So this is your R. And you have 1.2 million as your A sub 0, or your P value, or A sub 0. You can use A sub 0. But the continuous compound lets us know we're going to use this formula. Or in this case, I'll say A sub 0. And then that will be K. And then write a function to model the population with respect to T after this year. So that just means 1.2 goes here for the A sub 0, E, 0.025 T, and that's our equation. And then here, we're just going to put from 20 to 25, that's 5 years have gone by. So we'll put a 5 there. 1.2 E, 0.025 times 5. So this is about that million people. And then here we want to double, so we could just say 1.2 times 2. So we want to get it to double that amount, and we want to know the time. So then you can do that, divide 2.4 divided by 1.2. And then undo the E by taking natural log. And then dividing by 0.025. So T is about 27.725 years for it to double.